Okay, so this is just a short podcast of a worked example of the simplex method. Okay, so what I'm going to do is the actual example is taken from the booklet written by Kirk Lanfeld, which is available on the DLE. It's from section 2.4 and page 39 onwards. Okay, so we're doing a linear programming problem, and the problem we're going to look at a specific example. So we're going to maximize f equals 3x1 plus 5x2, and we have some kind of constraints converted into equalities. Okay, so one of the issues is we have essentially we have three equations and we have five unknowns. And so from the kind of graphical method of solving linear programming, I motivated the fact that the solutions are going to be at the corner, the feasibility region, or some kind of suitable multiple dimensional generalization. And essentially the simplex algorithm is going to, as long as you start at a feasible corner, it's going to loop through corners, choose a new corner that this case is going to maximize f. Okay, so that's what the algorithm is essentially going to do. We're going to start from a corner, a member of the feasibility region, and then we're going to have a couple of steps that's going to tell us a way to update, to move through this space to always increase f, the objective. Okay, so we're in the basic feasibility region. This is where the variables are allowed. Remember, the way it's set up at the moment, all the variables are positive. So if we end up, say, with an objective function, which is we're looking for the minimum, and we end up with 120 plus 3x1 plus 5x8, and we're looking for the minimum. The fact that x and any of the variables have to be positive tells you that if you increase either x1 or x8, that will increase f, and that tells you, because the x1 and x8 always have to be greater than 0, that 120 is the minimum, because you want to kind of, with f written in this form, the only way to make f any the smallest is to have x1 and x8 equal 0. And likewise, if you have an objective function like 120 minus 2x2 minus 5x3, and looking for the maximum, because x2 and x3 both have to be greater than 0, if those variables are anything other than 0, it'll decrease f away from 120, and this tells you that the maximum is 120. And however, often you're not so lucky. The objective function, if you end up with something with, you're looking for the minimum, that's 120 plus 3x1 minus 5x2, because this minus 5x2 is not in the form that we had up above, that all the coefficients are positive, that we have to do some manipulation. And essentially we go through the steps. We're going to use some of the equations, the constraints, to rewrite the objective function like this in terms of positive coefficients, to be up like this stuff at the top, and that's sort of the idea of the clever algorithm that allows you to do this. Okay, so just saying again, the strategy, if the objective is to find a minimum, we're going to try and use the equations we have to cast the objective function into a form like this, to be f equals a0 plus a1, a2, and ak, all positive, times these decision variables, and then the minimum value is set by putting xn1, xn2, xnk equals 0. Okay, and by the kind of jargon of linear programming, this means that the variables xn1 through xnk are non-basic variables because they're all set equal to 0. And we can compute how many non-basic variables there are by looking at the number of decision variables minus the number of constraints. That tells us how many non-basic variables we have, which have to be set to 0. Okay, so in the booklet that motivates this example, we're just going to look at the maths. The example comes from a window glass example from a factory, and x1 and x2 decision variables, batches of product 1 and product 2. But in the booklet, we've kind of converted this into kind of maths, and all kind of real-world motivation is lost. So we're going to try to find f equals 3x plus 1 plus 5x2, and we're looking for the maximum. And we want to kind of recast that in terms of some number minus some combination of the decision variables. And we have 3 constraints and 5 variables. Okay, so we're looking to maximize f equals 3x plus 1 plus 5x2, and we have these constraints, and f is not in the required form, so we're going to have to do some kind of manipulations. The first thing we need to do is check that we're in the basic feasibility solution. So if we set x1 equals x2 equals 0, then we solve these equations up here. So if x1 equals 0, we get x3 is 4, and similarly with x2 equals 0, we get x equals 12, x5 equals 18. These are all positive. So our starting point is in the basic feasibility region. And then the idea of the simplex algorithm, once it has a set of variables in the basic feasibility solution, it gives you an algorithm for constructing another basic feasible, another kind of corner of this this space. Okay, so I mean, what we have is we have the f, we have 3x1 plus 5x2, and what we want to do is recast this somehow into some number minus some combination of decision variables, and we have some equations, so we're going to essentially use some of these equations to rewrite this f. And the kind of algorithm goes, because this is 3x plus 1 plus 5x2, we're going to actually try and remove the x2 from the objective function. So because 5 is greater than 3, we've decided to use the equations to remove x2, so x2 is the in the jargon is known as the leaving variable. Okay, but if we go back again, so we have these equations, we can get rid of x2, so essentially we have 2 choices of possible equations. Okay, so this is kind of an algorithm, this is a set of steps. So the way it is, you normalize the equation so the x2 has positive coefficients, and then they say that the algorithm is you look at the equations when x2 is normalized to have a unit coefficient like this. You use the equation with the smallest right hand side. So I mean, just naively, if you didn't know about the simplex algorithm, you try 1 or 2 or both and see what happens. In this case, the algorithm tells the ratio test tells us to use this x2 plus 4, x4 divided by 2 equals 6 to remove x2 from the objective function. Okay, this thing is known as a ratio test. Okay, so we had so f is 3x1 plus 5x2, and we decided to remove x2 using this equation here by the ratio test. We substitute in 6 minus x4 over 2, and we end up with we collect terms. We end up here f is 30 plus 3x1 minus 5 over 2 times x4. Okay, and this is starting to look like we want. So we have a number, and then x4 is a minus, and then obviously we want to convert this x1 to also into some decision variables with a negative coefficient. So we've used one of the equations, so now we go back to our equations, and we have 2 possible equations to get rid of x1. And also I've done a little bit of manipulation to remove the x2 from the equations. So we have x1 minus plus x3 equals 4, and 3x1 minus x4 plus x5 equals 6. We do the same thing, we're interested in the equations with the coefficient of 1 by x1, and then we have x1 minus x4 divided by 3 plus x5 divided by 3 equals 2. So that's the equation just divided by 3. And then we use the ratio test again. We have these 2 equations for x1, and we use the equation, this one here, with the smallest right hand side. That's the ratio test. Okay, so we have the same thing again. The ratio test tells us to use x1 minus x4 divided by 3 plus x5 divided by 3 equals 2, and then we substitute that into the objective function we had before, which is f equals 30 plus 3 x1 minus 5 over 2 x4, and then we substitute this equation in here, collect up the terms, and you can see now we've got it in the form 36 minus 3 over 2x4 minus x5. So after 2 steps you've got it in the form of 36 minus 1.5 x4 minus x5, and we're looking for the maximum, and x4 and x5 have to be greater than 0, the way we set the problem up, and that means if x4 or x5 are greater than 0, they'll just decrease this f. So you can get the maximum when x4 equals 0 and x5 equals 0. Okay, so that tells us the optimal solution. And then originally we had 5 unknowns and 3 equations. Now with this we've set 2 of the variables equals 2, so there are 3 unknown variables, x1, x2 and x3, and we can solve our original equations to give us 2, 6 and 2, x1 equals 2, x2 equals 6, x3 equals 6, and we have the maximum of f is 36. And so to just go back the elements, we have a way of systematically moving through the corners of the solution, and we're eventually trying to rewrite the objective function to be this form of positive number minus these decision variables with negative coefficients. Okay, so I mean, this is a very bare bones example, so I've not done it. If you look in the books, a lot of the time they'll rewrite this in some kind of tableau, some kind of matrix notation. Since I'm mostly perhaps more interested in using kind of computers to do this, I think it's important to know it analytically, but I'm not going to test this in an exam, so I'm not going to get you to learn the kind of tableau method, but it's useful to be able to work a couple of the simplex ones by hand, just because well, if anything goes wrong with the computer program. Okay, so that's the end of the